So it's now that time in the course where we want to turn towards object-oriented programming, the main target of what we're going to discuss. So what we're really going to do today is look at the idea how to go from a structure to a class, and I'll explain what both of those are, and then look at the basic features of the C++ class, which is the core object that allows us to object-oriented programming. So the idea is to discuss our public and private data, access functions, constructors and destructors, member functions defined outside the class, and function return types. And then I will discuss a little bit at the end the idea of using vectors of objects. So, good. Let's think about what we are going to do. So the basic idea is the idea of an object, which is why we call it object-oriented programming. So what is an object? Well, you may think of a real object like an apple, a pencil, or a car. They're defined by a couple of things. Their properties, which are the nouns, and they are defined by the functionality, and which are really is equivalent to a verb. Some people would say they're also defined by their relations, but that's the thing that is not as well defined in object-oriented programming as in other places. We can extend this concept to how we store and manipulate data. A simple way to capture all the properties of an object, which actually originates in the C language, is called a thing called a struct. So a struct is just a bucket where you can put things in. So, for example, think about a particle object. We can define a struct to hold its properties, which would be data. For example, there would be a string, which would be the type, the mass, the momentum, and the energy. Those are very, very sensible ways, if you go to your particle physics course, to describe a particle, or particle at a movement with a given momentum and energy. So, that I can live with. I can then use this to define for every particle their associated data. So I could have a particle which is an electron. The electron dot type is the string electron. The electron dot mass is 5.11 times 10 to the 5th. The momentum, for example, could be 1 GeV, 1 times 10 to the 6th. The energy, which is in some sense a superfluous variable, can just be calculated from the mass and the momentum. Then we could also define a proton. The proton has a mass of about close to 1 GeV, and I could put some momentum in there, etc., etc. So that declares members of that object. In essence, right? Essentially, so we have defined objects that are defined as belonging to this struct. But the real thing is you probably want to do something with the data. I mean, just having data without being able to act on it is not what coding is all about. So let's pick the simplest idea. We want to print the data. So we could take a void print data function, which takes a construct particle np, etc., etc. And you can see what happens over there. So it takes a particle as an input and then does stuff to it. For example, it outputs all the information we have about it. Similarly, we could declare a function that calculates the Lorentz vector by just calculating the ratio of energy over mass, and that would be a really useful thing as well. Again, there's a construct over there. We almost always use a reference over here because these objects become complicated. There will be lots of copying going on if we didn't do that. So, if I show you a full piece of code, just to talk you through it a little bit. So essentially, we introduce some headers. In this case, I use CMath, which is a slightly unfortunate thing to have to use, but there are reasons for that. And then you got the struct particle, type, etc., etc. We can then print the data. We've just seen that function, the gamma. We can then just do what we've just seen, fill the data for an electron and a proton. Print the data for an electron, print the data for a proton, calculate some Lorentz vectors, etc., etc. And that is all a way to deal with a struct. Okay, that's fine. If you run that program, it outputs the information about the particle. It will export the Lorentz vectors as well. Some disadvantages of this method. The data for each structure must be defined outside the structure declaration itself. And it's not very easy because it makes it easy to forget to set a particular value. Right? It's also data is all available everywhere in the code. So if you make a coding mistake, you could alter the data or corrupt the data without realizing it. And a function acting with data are separate and require the data to be passed as a parameter. That doesn't feel the most elegant way. That separation is really what object-oriented programming tries to address. So how do we address it? So we try to address the data and their functions in one structure, which is the key, and this is exactly what C++ offers in the form of a class. Look at a very basic class defined on our particle structure. It's a class particle which has public members which are exactly the same as they were in the struct. We can replace just the particle definition in the code above and the code work identically. And there's a good reason for that, because C++ defines a struct as a special class where all members are public. And public just means that they're available outside the class itself. So the public keyword, this instructs the compiler that everything declared below it can be accessed from outside the class. Anything not declared public will be invisible outside the class, which you can also do explicitly by calling it private. There's a third P available, which is the case of protected. We'll discuss what protected does in the next week or two. Okay, let's modify the class to make everything private, just to see what happens. So, only changing the code, we run it like that. If you try to compile the code, you now get a large number of errors, as we are accessing private members outside the class. So that's the protection that private provides you. That's not a problem, it's an advantage. It allows us to keep data secure. But we still need a way to access these private data in a secure and safe and more sensible way. So, apart from the public native data, the main distinction between classes is that the class can and almost always will include functions to manipulate the data. In principle, a struct could do that as well, but since everything is public, it's not as necessary. So let us define one to set our type and one to print its value. So what we have over here is called a setter function. It sets the type of a particle to a given type, and we've got also a function that prints the type. So these are class member functions. These are functions inside the class, and they are called in a rather specific way. So they're public functions because you really want to use those outside the class. When a new object is created, we use the functions to refer to the particular object. We access these functions in a similar way to accessing the object's public data. It's myObject.myFunction, myArgument, making clear that the function is associated with the object, right? It's essentially the object.function. So, for example, string type electron, particle p1, p1.setType type, and p1.printType type. We only allow access to data through these access functions. We can protect our data from any undesirable consequences in designing these functions carefully. We struggle a little bit with setting all the variables. We do it in a very clumsy way, and it shouldn't totally surprise you since this is such a common task that there is a much better way to do this. There's two special functions for this, called a constructor and destructor, which can be user defined or can be supplied by the compiler itself. A constructor is a function that is automatically called when a new object is created. It's even more powerful when we combine this with default values, as we see in the next slide. A constructor can be overloaded to give different actions depending on arguments, so that allows me for different initializations. It has the same name as the class itself and has no return type, not even void. Its main use is to set values for the object's member data, and similarly a destructor function is used to destroy an object's member data. Let's look at it. So if we look at the same class we had before and we now add a destructor to the class and a constructor, first of all you'll notice that I've given default values for all the argument, which is actually quite useful because that really means that gives the indication what we want to do if we don't specify any variable. And that means the default constructor can just be said, well, set everything to the default values, which is what we say over here, which is an elegant way set a default constructor. It's not the way it has to be done, there's other ways around that as well. But for example, if we then want to have a parameterized constructor where we give all the arguments, particle type, particle mass, particle momentum, then that's 3 of the arguments, of course, then I can just initialize those 3 in what is called an initialization list over here, and I can also initialize the energy by an explicit calculation. That shows effectively that the energy is not independent, which is one of the weaknesses of the definition of our class. The destructor actually in this case doesn't do anything, and we just print out, which can be quite useful because it gives you an indication where elements get destroyed, which can actually be quite illuminating the first couple of times you use a destructor. And maybe even more than the first couple of times. So the first constructor, particle equals default, is the default constructor and will be called when we declare an object with no parameters. For example, if we say particle P1, which by definition calls the default constructor. In this case, the particle type will be set to ghost and its other data are set to 0. The destructor is called when a function exits, including main, for example, at the end of a program. And we can, for example, see that in this case that it will be called then. It's really useful when dynamically allocating memory. If we use new in the constructor, delete would typically go in the destructor, but it's good practice to include one because it helps us to understand what the code does. Note that we had these 2 different constructors where we made use of overloading. The parameterized constructor is well defined because it allows us to pass values to our data when creating our object. And it also computes the energy. So far, all these functions were defined within the class itself, for example the constructors, but we have not specified the details for print data. Such a larger member functions, including full detail, can often make the basic code look very clumsy and hard to read. The solution is often to put the implementation of such a member function outside of the class, or as we'll see later on, probably in a separate file. The important note is that member functions must be prototyped inside the class, and for example, we defined the function in the class in as natural a way as we could. Now, outside the class, we defined the function itself. So we've got a particle print data. So realize that we now need to prefix it with this name resolution operator, this double semicolon or scope resolution operator, which says which function we're actually defining over here. And then we have the same statements as before, still accessing the the private data of the class inside the function, because that's not a problem. The names of the functions defined outside are preceded with this class resolution operator. It tells me what function it belongs to. Without this name resolution, the compiler would assume the function to be an ordinary function, not a member function, and then it could not act on those private data members. Our member functions up to now have not returned anything, but this is possible as it is with normal functions. As a counterexample, we define the functions that return the Lorentz vector gamma. In the class, you would write double gamma return energy over mass, and in the main program, I can actually use electron.printdata, proton.printdata, and I can do electron.gamma in the output of the gamma vector, and that would then output a double automatically. So that was all fair and good. So let's look at another piece of code, which you will see in the whole definition of this thing. Let me do something really intriguing. I define a vector, but rather than an int or a double as we saw before, I now define it as a vector of particles. The power of this vector technology built into C++ is that you can easily do that. You can do it with any object, and then I can actually add one by one this object to the function. So pushback adds something to the end of an array, and then I iterate over the data with an iterator. Here is probably the first use you ever see of the auto function. I mean, auto is actually a way, it really is the way not to have to write down the whole declaration. From this assignment over there, the compiler can work out what the type of particle is. So calling it auto really means give it a type that corresponds to whatever the right-hand side is. So you don't have to type the incredibly long statement vector, particle, iterator, etc. Okay, so that's a rather long statement to make. So the particle iterator is less than the particle data.end, and then you go plus plus that, and then you do particle iterator. And here I've got an error notation, which you may not have seen before. That's actually nothing more than star dot. So star dot is such a common combination where you dereference a pointer and then take a member of it, that we have a special symbol of saying dereference and take the member in one step, because essentially it makes the code more readable. And then we can just print out the gamma function as well by exactly the same way. So that looks very sensible to me. It uses the refinements of user vector. There are other containers which later on a list might be a nice one to use as well. And we can use iterators over the data to output all the information. The reason to use iterators as well, again, is that that would work for any container, not only a vector. I use the arrow operator as I discussed over there to dereference the object. And the iterator is like a pointer. That's what I really want to say. So, let's give you a buzzword summary. A class is the set of rules used to define our objects. It specifies which type of data and functions are created and their scope, either private or public. An object is an instance of a class. Each object will have its own set of data. A member refers to either data or a function belonging to a particular class. For example, a constructor is a member function. Member functions are sometimes also called methods. They're both used. A constructor is a special function called when a class is instantiated, usually to initialize an object's member data. If not user-generated, the compiler will generate one for you. A destructor is the function called when an object is destroyed, usually automatically when exiting a function, which really means is what happens when we say the object goes out of scope, so you can no longer access the object, then it clearly needs to be destroyed. If not user-generated, again, the compiler will generate something for you, which may or may not satisfy you what you want. And that's it for this week.